team with us, who's a professor of biostatistics at American University of Beirut, and also at King Abdullah International Medical Research Center. He's been working with the Saudi Critical Care Trial Group for several years and has been essential in many of the high impact publications from the group, and it's our honor and pleasure to have him today with us. He's gonna introduce to you. He's gonna go through basic statistics that are essential for us to understand the literature, and as well as for many of us who are doing the research projects to have the understanding needed, basic understanding for statistics. So welcome, Dr. Hani. The floor is yours. I think we're gonna have maybe 50 minutes for a presentation and have some time for discussion. I would like to ask people to keep their microphones on mute all the time, please, very important. And questions can be put in the chat box, which I don't know, do you have a chat box? If not, we can open the microphone later at the end. I don't see a chat box, but we can open the microphones at the end. But for during the presentation, keep the microphones off. Dr. Hani?
Dr. Arabi, thank you very much for the introduction. It's a pleasure to be presenting to you today. Is my voice clear?
Yes, clear.
Okay, perfect. The last thing I want to ask you is to have a host to be able to present, to share my screen. I just need to be sharing my screen. Somebody can give me host privilege.
Rose, can you give the host privilege to Dr. Hani?
Yes, Dr. Yasin.
Yeah, can you give the ability to share slides from Dr. Hani? Make him host.
Okay, Doctor.
Please, the newcomers, please mute your microphone.
I'm still not able to share my screen.
Just wait, Doctor, just wait. I will.
All right.
Okay. It's okay now, Doctor? Okay.
All right. All right. So just to confirm that everybody is able to see my screen and to hear me well. Okay, perfect. Yes. So I'm going to start. I'm going to have around 50 minutes. The objective of this session is to go over different concepts in statistics. What I'm going to be doing is going from the very basic to somehow advanced. I'm going to cover some terminology that we usually use. Some of the things that I'm going to be discussing might be basic for you guys, but I like to give a comprehensive overview of statistics, which is usually used in most of the epidemiological studies that we carry out. So I will start by saying something about statistics. So what is it? It is a field of science concerned with not only the analysis of the data. So if you look at the definition of statistics, it is the collection, organization, summarization, and analysis of data. And this is something we call descriptive statistics. And at the same time, it is drawing inferences about a body of data when only a part of the data is observed. And this is called inferential statistics. I will be talking about these two types of statistics in a few minutes. One piece of information that we usually miss is that a statistician is not only involved when the data is collected and entered into the computer, to punch a few buttons and get some results out of it. A statistician will be able to help in even designing the data collection forms and collecting the data and cleaning it and managing it and so on. So it's very important to have a statistician involved in your project early on. So what is biostatistics? It is the application of statistical methods to biological and health-related questions. And as I said, it is a component required for the completion of any epidemiological study. There are three terms that I like to go over. One is the population, and the population is usually the largest collection of entities for which we have a special interest at a particular time or while doing a study. It's very important to identify the population because whatever study you do, you take a sample from the population. And whenever you want to generalize the results of your study, you have to understand what are you generalizing to. So you usually target the population that you started with. So for instance, if we're talking about ICU patients, then the population is all ICU patients. And the sample we take to study to carry out our study eventually is generalizable to all ICU patients. Now, how do we select a sample? We select a sample by different ways. The most or the best way to select a sample is by random selection, where each person in the population has an equal probability, we call it, to be part of the study. In other words, we try to avoid convenient sampling or a method of selecting a sample based on preference or convenience and so on. So if you sit with a statistician, you will hear the term variable every now and then. So what is a variable? A variable is a characteristic of the subjects under observation that takes on different values for different cases. For instance, if we're talking about age or gender or blood pressure or physical activity, mortality, and so on, each one of these is a variable. A variable by definition is something that varies, that changes. It doesn't mean that it has to change over time because, for instance, gender does not change over time, whereas it has to change or it has to be different between different participants of the study. So if I'm talking about, let's say, prostate cancer, gender is not a variable because all subjects are males. But if I'm talking about, let us say, ICU patients, then I might have males or females, and accordingly, okay. So what I was saying is a variable is something that changes between different subjects, and it is every piece of information I collect on the sample that I have. Now, there are two types of variables. One is called quantitative variable and one is called qualitative variables. So what does a quantitative variable mean? It is a variable that conveys information regarding amount. So for instance, if I measure the weight of a patient, it is a quantitative because the answer will be reflecting on a measurement. Whereas a qualitative variable is a variable that consists of categorization. It has nothing to do with quantification. For instance, if I'm talking about gender, male, female, I cannot quantify gender, but I can put people into either males or a females category. Now, these are some examples of categorical and continuous variables. Categorical or qualitative variables, qualitative, such as death, yes, no, gender, male, female, blood groups, or education. Continuous variables or quantitative variables are such as age, blood pressure, and weight. Somebody raised their hand. What does it mean? Do you want to ask a question? Or do you have anything to say?
I think we'll keep the questions to the end.
Okay, all right. So, all right, so after we talked about the variables, why is it important to talk about or identify the type of variable or the piece of information that we're collecting? Because as you will see in the next few slides, any statistical analysis that we will be doing will be dependent on whether the variable is a quantitative or qualitative, or categorical or continuous. So if a variable is categorical, we deal with it in a way, but if it is a continuous variable, we deal with it with a completely different way. So that's why it's important for us to identify the type of variable. Now, if I want to talk about data analysis, there are 3 levels of analyses that we usually use, 3 levels of statistical analyses that we usually use. One is called univariate, one is called bivariate, and the third is called multivariate. So if we assume that variate is something relating to a variable, when I talk about univariable or univariate analysis, it means I'm taking only one piece of information. And this piece of information, I'm trying to analyze it. Just one second. So univariate analysis is an analysis that I do when I'm talking about one variable. For instance, if I tell you what is the average age of patients in the study, I am dealing with only age. But sometimes I want to do associations, or I want to link 2 variables with each other. In other words, I want to see who is dying more, the older or the younger age. This is a very basic question. But the point here is I am doing 2 variables, and it's called bivariate analysis, and I'm associating the age and mortality. So these are 2 variables that I am analyzing together to get an association. The last part is multivariate analysis, and it means I'm doing multiple variables with each other. And why do we do that? Because even if I'm interested in age and mortality, there are other variables that might affect mortality, such as gender, or such as hypertension status, or diabetes, or whatever. So I want to control for the noise that I'm getting when I'm doing the association between age and mortality. So my interest is age and mortality, but I want to add to this type of analysis some other variables that might affect mortality, such as diabetics, being diabetic or not, and gender, and so on and so forth. So to sum up this slide, 3 levels of analyses: univariate, bivariate, and multivariate analysis. Now, I will start with the univariate, and we call it usually descriptive analysis. And this is what I talked about at the beginning of the session. Descriptive analysis is the very first level of analysis that we usually do. Now, as I promised you, all analyses are dependent on whether the variable is categorical or continuous. Now, I'm going to start with the descriptive analysis for categorical variables. Now, how do we summarize or present the results of a categorical variable? Let's say gender, male, female. Now, somebody might tell me, I can present gender by numbers. I can tell you I have 300 males and 200 females. This is good. Some other people might say, let us present it as percent, saying 60% are males and 40% are females. Now, not to go into details of why there are some limitations of presenting each one alone, but the bottom line is that presenting both is important, because the number gives you the volume or the sample size, and the percent gives you an easy way to differentiate between them. So what we do is we present both number and percent. And there are some graphical presentations, such as a bar chart or a pie chart, that we can do for categorical variable. So for instance, this is a study about a clinical trial. I don't care about the study itself, but I just want to show you the results. Here, if you look at the number of men, I have an intervention group and I have a placebo group. Now, you see that I have 216 in the intervention and I have 213 in the control placebo. We need to mute Robin Thomas, I guess. All right, so I have an intervention and a placebo, 216 in the intervention, 213 in the placebo. And the way we presented the gender is by putting a 97 males, which represents 45% in this group, and 124 out of 213, which is 58%. So the bottom line is whenever you want to present any categorical variable such as this one or this one, primary site of cancer, or histological grade, or any other categorical variable, we usually put a number and a percent. Now, this is the same. For graphical presentation, this is called a bar chart. What does a bar chart mean? It gives you the button. It gives you the. We need to mute this. Somebody's unmuted. Please make sure you're repeat us. Okay. Dr. Yassin. Okay. Unmute. Okay. Now you can hear me, I guess. Back to the slide. This is a bar chart. What does a bar chart mean? It means I have the x-axis, which presents the variable itself. And here I have a percent, for example. And the reason why we call it a bar chart is because we have categorical variable, first line, second line, third line, fourth line, or overall. And we have a space between each of these two lines. And the reason we have this is because there is no continuity into it. This group is completely different than this group. So there is no continuity into it. And that's why we call it a bar chart. It's reflecting some bars, which shows visually what is the differences between the different groups. Now, this is a pie chart. It's exactly the same as a bar chart, but instead of having bars, I have slices of the pie. Of course, you know that this is 100%, and according to this, I can put the response rate of 36%, which represents this slice, survival, and so on and so forth. Now, if I talk about the continuous variables, which is the second type of variables, how do we describe it? Now, of course, we cannot put a number and percent because there is continuity. Let us take an example of systolic blood pressure. Some people might have 120, 121, 122, 123, and so on and so forth. So there are so many answers that we might get from the systolic blood pressure. Now, how do we best summarize this continuous variable? We have something called central tendency. What does central tendency mean? It means that I want one measure or one answer or one piece of result that gives me a summary of all the variable itself. So the best way is to do the mean, the average. There is another one, which is the median, and the third one, which is the mode. The most frequently used one is the average, which is the mean. Now, how do we calculate the mean? It's I'm sure that all of you know, but we add up all the data, then divide by the sample size. So I add the systolic blood pressures of all the people in my sample, and I divide by how many people do I have. In this example, I have 5 patients. These are their systolic blood pressures. I add them up, I divide by 5, and then I get a 99, which is the average systolic blood pressure for this. Now remember, this is a continuous variable. Now, this is the formula. It's the summation of Xi, meaning the systolic blood pressure of all the patients, divided by the sample size. And this is also called the mean. It is sensitive to extreme values. What does it mean? It means if I have one patient who has an extreme value, let's say 200 or 220 blood pressure, the whole average will be shifted. So it will be affected by this value. Now, uniqueness is another characteristic of the average, and simplicity because it's very simple. The median, which is the second measure of the central tendency, is the number that falls in the middle of the data. So what do? I order my data in an ascending or descending order. Then I take the number that is in the middle. So in this case, it is 95. There are 2 people below, 2 people above. It means it is the middle value. Now, one disadvantage of the median is that it ignores all the data, but takes only one piece of information. Whereas in the average or the mean that we discussed a minute ago, we take every single patient into consideration. Every single patient contributes to the calculation of the mean. That's why the mean is a better measure of central tendency. Now, a good thing about the median is that it is not sensitive to extreme values. So if I have a person who has 200, still the median will be 95. So one advantage or one good thing about the median is that it is not affected by extreme values. If I have an even number, in this case, I have 6 people, I will take a virtual number in the middle where in this case, it's 102.5, where I have 3 people below, 3 people above. Now, properties, uniqueness, simplicity, and not affected by extreme values. And the last one is the mode, which is the most frequently occurring number. In this case, I have 1 time 80, 1 time 90, and 2 times 95, 1 time and 1 time, and thus the mode will be a 95. Now, if I tell you I would like to summarize systolic blood pressure, for example, and you give me the average, would I be having a good picture about the systolic blood pressure? No, I will not. Why? Let me tell you. Because look at these 2 examples. These 2 examples have the same number of subjects.
Diba yung sa ano nun dati, nabalita nun?
Okay, so in this example, assume that I have 9 patients in each of these 2 groups, and I have the measurements, let's say age in this example, 21, 22, 23, and so on and so forth. And another example, 9 patients with all these values. If you look at the mean, if you add them and divide by 9, it will be 23.6. If you look at the mean in the other group, it's 23.6. The median here is 23. The median here is 23. So you would assume they are exactly the same group. But in fact, they are. What is different between them? The difference between them is that the distribution is different. And this is what we call measures of dispersion. So on top of the average, we need to provide something that's called a dispersion. And in this case, it is the range, variance, or standard deviation. What is the range? The range is the maximum minus the minimum. So I want to know over what does this sample range? What is the minimum value? What's the maximum value? And this is called the range. But the problem here is that I'm ignoring all the middle values. I'm only taking 2 pieces of information, the minimum and the maximum, and that's why it's not a very good measure of dispersion. The second thing is the standard deviation. I'm pretty sure you might remember it. What is a standard deviation? A standard deviation is, this is the equation for it, the formula. It's xi minus x bar squared divided by n minus 1. In 1 minute, I'm gonna go over what does it mean. Xi minus x bar, it means each patient, I get the deviation or the difference with the mean. So each patient will have a difference from the mean. I square it to get rid of the negative values because some people are less than the mean and some people are above the mean. So when I get the deviation, I square it to get rid of the negative sign, and then I divide by sample size. So in theory, what I'm getting is the average deviation. So when I say average deviation, it means on average, each of these subjects or patients have this value of the deviation from the mean. I'll give you an example. In this example, I have the 5 systolic blood pressures. I take the first one, 120, minus the average squared, plus 80 minus 99, which is the average squared. And in each one of these, there is the deviation that I'm talking about. And then I add all the deviations, and then I divide by the sample size, and then I square root it to get rid of the square sign, and I get a 15. What does 15 or almost 16 mean? It means each of these 5 patients are on average 16 units away from the average. Some of them are 30 units away, some of them are 5 units away, but on average, they are 16 units away from the mean. Now, the bigger the S or the standard deviation, the more variability we have. So if I have a data that ranges for systolic blood pressure between 100 and 200, it has bigger standard deviation as compared to a data where it ranges from 120 to 180 and so on. The S, or the standard deviation, measures the spread above the mean. If it is equal to 0, it means there's no variation. All of them are the same. And the unit of the standard deviation is the same as the unit of the data. Now, this is an example. I have the median in this case for a continuous variable. I have the median and the range. But for something else, I have the average and the standard deviation. Now, this is a graphical representation. We call it a line chart. What does a line chart mean? It means that they are connected with each other because there is a continuity into the answers that I get. It's not like the categorical variable where each group is alone. Here, there is some continuity. Now, there is something that we usually use. It's called quantiles and percentiles. What does quantiles mean? It means, or percentiles, it is the pth percentile, or the p% of the sample that are smaller than this value. So if I tell you I have a 25th percentile, it means the lowest first quartile, which is the first 25% of the data. 50th percentile, it means 50% are below this value, and it's similar to the median, which is 50% below. 75th percentile is called the third quartile and denoted as Q3, which means 75% of the data is below this value. So sometimes when you're reading a paper, you might come across something we call IQR, which is interquartile range. And the interquartile range is Q3 minus Q1. I will remind you, Q3 is the 75th percentile, Q1 is the 25th percentile. In other words, the Q3 minus Q1 is giving you the middle 50% of the data. And remember, all of this, we're doing it to see how wide my data is. Now, this is a box plot. Usually it is a graphical representation that we put for continuous variables. Again, this is the middle box, which is the box plot. Q1, which is 25%. So I know that 25% of my data are less than this. 50% of the data is less than this, and 75% of the data is less than that. Now I'm done with the descriptive statistics. I'm going to move to the inferential statistics. What is inferential statistics? It is the following. Before I go into that, I want to talk about probability. So what is a probability? A probability is the percentage or the chance that something will happen. It ranges from 0 to 1, 0 meaning impossible, 1 meaning for sure it's happening. So why is it important? Because it's applied at all levels of biostatistics. It's used at so many different levels. For instance, if I tell you 4% chance of a patient dying after admission to an emergency department. Now, what do we mean? What we mean is out of each 100 patients admitted to the emergency, 4 will die, whereas 96 will be discharged alive. So this is a probability. If I tell you 1 in 1,000 babies are born with a certain abnormality, it is a probability. Incidence and prevalence, meaning what are the chances that a person will have the disease, they are also probabilities. This is something else I will talk about in a few seconds. Now, why do we conduct research? This is the most important question. We conduct research to answer questions. What type of questions do we like to answer? We answer questions about a certain population. So assume I have a population such as ICU population, ICU patients, and I want to answer a certain question, their quality of life, their survival, their length of stay in the ICU, and so on. All of these are different research questions, which I might need to carry out a research project to get an answer for. So what do? I take a sample. Now, out of this whole population, I take a sample, hopefully that it will be a representative sample. And then what I do is I carry out my analysis on this sample. So you ask a question about the population, I take a sample and I get the results on the sample. But have I answered your original question about the population? No. What do I need to do? I need to use the results of the sample to generalize my conclusions to the population. And this is called inference. And that's why we call it inferential statistics. There are two types of inferential statistics. One is the confidence interval and one is the p-value, and I'm going to go over it in a few minutes. Since we are not taking the whole population, we have to draw conclusions on the population based on results we get from the sample. This is what I talked about in the previous slide. Say we want to estimate the average systolic blood pressure of patients admitted to the emergency department. This is a simple question, might not have a lot of clinical sense, but I just want to highlight how do we do the inferential statistics. Now, again, the objective is to estimate the average systolic blood pressure of a certain group of patients. Other more complicated measures might be quality of life, risk, and so on. So what do? We take a sample. I took a sample of 291 patients admitted to the emergency, and I calculate the mean and standard deviation, which is the descriptive statistics we talked about, and assume that I found that the average is 144 and the standard deviation is 35. But what are these answers or these results pertaining to? Are they relating to the sample or the population? Of course, it is the sample. So this 144 average is for the 286 people only. But I'm interested in the whole population. So what do? I have to do inferential statistics. So the next step is to make a link between the estimates we observed from the sample and those of the underlying population. What can we say about these estimates as compared to the unknown true ones? What are the unknown true ones? These are the population measure. So there is an average systolic blood pressure for the whole population, which I do not know. What am I trying to do in my study? To estimate it. To estimate it based on what? Based on the sample that I got. In other words, we are trying to estimate the average blood pressure for all patients who are admitted to the emergency. So there are two issues that we can do. Either estimate the value of the population parameter, which is the average blood pressure of the whole population. It's done by interval estimate, or evaluate a hypothesis. Let me go to the next one. The first is called a confidence interval. What does a confidence interval mean? Confidence is how sure you are, how comfortable you are, how certain you are. And how do we measure confidence? We measure confidence by percent, probability. I can tell you I'm 100% confident, or I'm 50% confident, or I'm whatever confident. An interval is a measure between, or an interval, or an interval is something between two numbers, right? So if I give you 120 and 130, the interval between 120 and 130 is going to be a confidence interval for the systolic blood pressure, for example. So how do I do that? I'll take you straight to the calculation. But before I do that, you might remember that in any distribution, if it is a normal distribution, if you do not remember it, that's fine, I'm giving it to you now. In any normal distribution, this is a normal distribution because it looks very nice and it's symmetric and it looks amazing actually. So in any normal distribution, 95% of the data falls between two standard deviations. So the average 125 minus 2 times 14, which is two standard deviations, and 125 plus 2 standard deviation, you will have 95% of the data. Now, if I subtract and add 1 standard deviation, I will always get around 68%. If I subtract and add 3 standard deviations, I'll get 99.7%. So this is a basic probability concept that we use when we calculate a confidence interval. So look at this. 144 is the average. If I add and subtract, this is a rounding for 2. You remember here, what we did is 2 standard deviation below and 2 standard deviation above will give me a 95%. So if I say average plus 2 standard deviation, this is the standard deviation, the 35, and 144 minus 2 times standard deviation, I will have around 95% of the data. Now, in this case, I selected a sample, I got a 144, and this confidence interval ended up to be 140 to 148. Now, let me try to explain to you why do we divide by sample size. We divide by sample size because as we take more people into our study, our estimation will be better. What do I mean by our estimation? 140 to 148 is my estimation of the population blood pressure. In this case, I'm telling you 95%, I'm sure 95% that the population systolic blood pressure is somewhere between 140 and 148. I'm not sure what exactly the value is, but I can tell you that it's between 140 and 148. Now, this is a good start, right? Because I will never be able to give you one number for the population unless I take the whole population. If I take the whole population, I can get you one average blood pressure. We will never do that. So what we usually do, we take a sample and eventually we give a confidence interval. In this case, I'm telling you, I'm 95% sure that the true population systolic blood pressure is 140 to 148. Now, what does it mean? 5% chance that it is not within this interval. But researchers agreed that, you know what, 5% error, which is the 100 minus 95, 5% error is okay to live with. I can survive with a 5% error. Now, let us go back to this. As I take more people in my study, if I take 1,000 people or 10,000 people, my estimation or the strength of my study will be better. So what do you expect to have in here? You expect it to be narrower. The more people I get, the better the estimation will be by having a narrower confidence interval. And this is why if you increase the sample size, this whole thing will go down, and then 144 plus minus a smaller number, thus it will be a narrower confidence interval and it will be more precise. If I have a smaller sample size, very small, if I take only 10 patients, this whole thing will be big, large, then I'm adding and subtracting a big value or large value, and thus the confidence interval will be wide, meaning it's not very helpful. So this is the confidence interval. Now the 95% confidence interval, thus if we repeat the sampling procedure 100 times, it will be correct 95 times, but it will be wrong 5 times. Now, are all confidence intervals 95? No, I might have a 99% confidence interval or a 90% confidence interval, but researchers agreed, as I told you, 95 is a very good level of confidence, or 5% error is affordable to have in a study. Now, this is a study on antibiotics and risk of prostate cancer. You see here a relative risk of 1.69, and this is the confidence interval. Now, let me go over, I'm sorry. Okay. I need to tell you about the relative risk, but I'm going to give it to you in the next few slides. But before I do that, I'm going to talk about the p-value. So what does a p-value mean? A p-value is a probability. A probability is related to another type of inference. It's called hypothesis testing. What does a hypothesis mean? A hypothesis is a statement, any statement you can come up with. And it might be true or it might not be true. And the objective behind the study is to confirm it or deny it. So we want to evaluate a hypothesis about a population rather than estimating it. In the confidence interval, we estimated it. And the p-value, we are evaluating a hypothesis. Let us take an example. Back to the previous example of the blood pressure of the emergency department, we want to make an inference. Assume that the normal blood pressure is 120. So I can put two statements. The question is whether the average blood pressure for patients admitted of the whole population is 120 or not. This is my question. And accordingly, I put two statements. One is called null hypothesis, and another one is called alternative hypothesis. So what are these two hypotheses? The null hypothesis is a statement that says no. No difference, no association, no effect, no correlation, no increased risk, or whatever it is. The opposite of this null hypothesis is the alternative hypothesis, which is saying it is disagreeing with the null and saying, yes, there is a difference, there is an association, there is an effect, and so on. Now, the whole objective to decide which of these hypotheses is true. We take a sample. If the data is consistent with the null hypothesis, meaning it's supporting the null hypothesis, then we say we do not reject the null hypothesis, and our conclusion will be no difference or no statistically significant difference. I'll repeat it. If the data is supportive of the null hypothesis, then we say the null hypothesis is true, meaning no difference or no significant difference. Now, what if the data is not consistent with the null or it is supportive of the alternative? meaning there is a difference, the conclusion will be, yes, there is a significant difference in the association or significant effect or significant correlation or whatever it is. Now, let us take the example. The null hypothesis is the average equal to 120. Average of what? Average of the population. Because I'm doing the hypothesis on the population, not on the sample. The sample, I know exactly what the average was, but the population is the thing that I do not know, and I do a hypothesis on it. The alternative is that the average of the population is not equal to 120. How do I answer the question? I take a sample and I find it to be 144. Now, can we consider the 144 consistent with the normal value or not? We have to calculate a probability. This is the distribution. This is the null hypothesis. If I get my sample average close to this, it means it's supporting the null. If I get it away from the null, it means I accept the alternative, meaning there is a significant difference. And this is an illustration. If my average, irrespective of the number, if the average is in this huge bulk here, then you can conclude that it is supporting the null, and thus I conclude no significant association. If the average is far away, then it is not supportive of this number, 120, and I say there is no significant, there is a significant difference. Now, can you mute yourself, please? Now, anything in the middle, it will support the null hypothesis. Anything at the extremes, it will support the alternative hypothesis. Now, how do I decide whether my sample supports the null or the alternative? By getting a probability. The probability is called the p-value. If the p-value, it's used to calculate the probability. The probability is called a p-value, and what does it mean? If the p-value is small, then this is taken as evidence that it is unlikely that the null hypothesis is true. We reject the null hypothesis. What does a p-value being small mean? Anything less than 5%. You remember the confidence interval? We said the error was 5%. So anytime I calculate the p-value and it is ending up to be less than 5% or 0.05, it means the sample is at the extreme, or I'm accepting the alternative hypothesis, or I'm saying there is a significant association in my study. If the p-value is high, it indicates that most probably the null hypothesis is true, meaning no significant association. And what do I mean by high? It means that it is more than 5% or more than 0.05. I'm going to skip this part, type 1 error and type 2 error. I'm going to go straight to the different tests that give me a p-value. Now that you understand that the p-value is a probability, less than 0.05, it means significant association. More than 0.05, non-significant association, or there's no association. I need to see, how do I calculate this p-value? How do I calculate it? There are different statistical tests. And all of these tests, chi-square, one-sample t-test, independent t-test, and correlation, are dependent on what type of variables are we dealing with. You remember at the beginning of my session, I told you all statistical analyses are done according to the type of variables. So now I'm talking about bivariate analysis, which is two variables at the same time. Now, if I have two categorical variables, for instance, male, female is a categorical variable, and I'm associating it with mortality, which is yes, no. I have two categorical variables. I calculate the p-value by doing a chi-square. Now, if I have two continuous variables, such as length of stay in the ICU and, I don't know, quality of life, okay, both of them are continuous variables, then I do something else called correlation. What about if I have a categorical and a continuous? For instance, I have an intervention group, a placebo group. This is a categorical variable. And the continuous is quality of life. Quality of life is measured on a continuous scale. Then I do a family that's called a t-test. The most frequently used one is independent t-test, and another one is ANOVA, which is analysis of variance, which I will show to you and give you the difference between them. Now, this is an example of a clinical trial. I have an intervention group and a placebo group. If I'm looking at gender, remember, I have categorical variable, male, female, placebo or intervention categorical as well. So what test do I use? I use chi-square test. What is this P? This is the P-value. Let us take this. The null hypothesis in this example is that the proportion of males in this group in the intervention is equal to the proportion of males in the placebo group. What about the alternative? No, they are not equal. What did I find? 47% versus 43%. Now, is this difference important, significant from a statistical point of view? I have to calculate the p-value. What is the p-value that I got? It was found to be 0.66. How did I calculate it? By a chi-square test based on what I showed you a few minutes ago. Now, is it a significant association? We agreed that anything above 0.05 or 5%, it indicates a non-significant association. In this case, it's 0.66 or 66%. Thus, I agree with or I accept the null hypothesis, and I will say there is no significant difference in gender between intervention and placebo. Now, what about this example? If I'm talking about the average age, is it significant or not? In this null hypothesis, the average age in the intervention is equal to the average age in the placebo. The alternative is no, they are not equal to each other. I calculate the p-value and I find it to be 0.533 or 0.5355. How did I calculate it? I have one categorical, which is intervention placebo. I have another continuous, which is the age. And accordingly, I use a t-test. The p-value is 0.53 or 53%. Thus, I accept the null hypothesis, meaning there is no significant difference in age between both groups. Now, this ANOVA, it's called analysis of variance. It's exactly the same as the t-test. But remember, the t-test was between only two groups. So the categorical variable was two groups. This is a study that had three groups, tertile 1, tertile 2, and tertile 3. So I have three groups rather than two. And if I'm interested in the age, in this example, I found 54 average age for the first group, 48 for the second, and 54 for the third. I want to see if there is a significant association. And the null hypothesis will be that the averages are equal to each other. And the alternative will be that they are not equal to each other. Again, the p-value in this case was 0.02. How did I calculate it? By ANOVA. ANOVA, analysis of variance. And accordingly, it is 2%, which is less than 5%. Thus, I conclude that the alternative is true. And there is a significant association between age and these tertiles. Now, this is the 2x2 table that I wanted to talk about. This is exposure. Let me go. So this is how we do an association between two categorical variables. Those who are exposed, such as intervention, I see what is the risk of their outcome. It is A over A plus B, and it gives me a probability. And among those who are placebo, non-exposed, it will be C out of C plus D, which is the probability. If I divide these two probabilities by each other, I get something like a ratio. In this case, prevalence rate ratio or relative risk ratio or incidence ratio and so on. I have three scenarios. If the first prevalence of the outcome in the exposed is equal to the prevalence of outcome in the non-exposed, then the ratio will be 1, meaning there is no association. If the prevalence of outcome in one group, the exposed, is more than those who are non-exposed, the prevalence rate ratio will be 2, for example, meaning they have the double the risk or double the chances or double the prevalence. If it is less, it is 0.5, meaning they have less probability. Let me give you an example. This is the prevalence rate ratio or relative risk or odds ratio, for example. Now, whenever it's equal to 1, it means there is no association. It means the probability in one group and the other group are equal to each other. And when we divide them by each other, it's 1, then it means there is no increased risk. If it is less than 1, it means the exposed have lower probability as compared to the unexposed, meaning it is protective. The exposure reduces the risk of the outcome, mortality, for example. If it is anywhere above 1, it means that those who are exposed have a higher risk as compared to the unexposed, and that's why it increases the risk of the outcome. In this example, I have 2 out of 22, which is 9%, 4 out of 36, 11%. If I divide 9 by 11, it means 0.82. It means this intervention protects against or reduces the chances of having the outcome. This is an example of vitamin E in the primary prevention of cardiovascular disease. I still need maybe 5 minutes. This is an intervention and this is a placebo. If I'm talking about myocardial infarction, I calculate relative risk. It's exactly the same as the prevalence rate, but for a different study design. In this case, I found it to be 1.01, meaning it's almost 1. So was the p-value significant? No. It means there is no significant association between the intervention and the myocardial infarction. What if I'm talking about cardiovascular death? I found it to be 0.76 with a p-value of 0.03. 0.76 meaning it's protective. Those who are in the intervention are at lower risk of dying out of cardiovascular reasons. Now, is it significant? Yes, 0.03 is less than 0.05. So I conclude that there is a significant reduction in the risk of cardiovascular death among those who take vitamin E. Now, let me take the third scenario, which we talked about. We considered the categorical, we considered the categorical, we considered the categorical continuous. We have still remaining the continuous. So a continuous variables, we measure it by correlation, and this is called linear correlation. It is represented as R. It ranges between +1 to -1. +1 means a perfect positive correlation. -1 is a perfect negative correlation. And this is an example. Look at X and Y. Both are continuous variables. And in this case, I plot these people and there's a perfect correlation. As X increases, Y is increasing. And that's why R is 1 + 1, perfect, positive. As one increases, the second increases. In this case, example 3, as one increases, the other is decreasing. And it is -1 because it's perfectly correlated. In these two examples, they are positive and negative, but this is not perfect and this is not perfect. So in this case, it is -0.66, and in this case is +0.66. The bottom line, this is an example of a correlation between two continuous variables. The null hypothesis is that the correlation is equal to 0. The alternative is not equal to 0 because 0 is a value which tells you there is no association at all between the two continuous variables. The correlation was found to be 0.31, meaning it is positive, but the p-value is less than 0.01, meaning it's significant. Thus, I can conclude that these two variables are positively, significantly associated with each other. Now, I still have 3 more slides. This is an illustration of what tests do we use. This is the exposure, this is the outcome, first variable, second variable. If I have two levels such as gender and mortality, I use chi-square. 2 levels, more than 2 levels, but still categorical, I use chi-square, and so on. All of these are chi-squares. If 2 levels and continuous, I use a t-test. Or 2 levels and continuous, I use a t-test. If more than 2 levels and continuous, as I said, we use ANOVA, or the opposite here. And finally, if it's continuous and continuous, it is a correlation. Now, different types of statistics. There are 2 types of statistics that we usually talk about. One of them is called parametric, one of them is called non-parametric. You see all of these tests that we have discussed, the chi-square, the t-test, the ANOVA, the correlation, all of them are called parametric testing because there's a certain foundation for the distributions. People or statisticians were able to define these distributions and they were able to calculate the p-values. But sometimes, if I have a small sample size, if I'm doing a study on 10 patients or 15 patients or 20 patients, it's very unlikely that a good distribution will be established. And that's why we carry out another set of analyses called non-parametric testing. The objective of this slide is to show you exactly the same set of tests, but these are the non-parametric. I'm not going to go over them. I just want to tell you there's a test called Fisher's exact test, Fisher's test, which is similar to the chi-square test. And we use it when we have 2 levels by 2 levels. So all what I need from you is if you read a test called Fisher's test, you should understand that it is a test that calculates a p-value between 2 categorical variables. Or I have Mann-Whitney for 2 instead of t-test, or Kruskel-Wallis instead of ANOVA. And there is correlation, it's called Spearman correlation. Finally, I have the multivariate analysis, and we talked about it at the beginning. Multivariate analysis is when I do the association between 2 variables and I put in or consider or adjust for or take into consideration different variables that might affect the outcome, such as demographic or past medical history or lab results or whatever. So it is a mathematical modeling where the confounders, which are the variables that affect the outcome, are included as variables in the model. Mainly, we have 2 types of regression analysis or multivariate analyses. One is called linear regression, one is called logistic regression. I'm not going to go in details over them, but I just want to show you the last slide that I have. Under logistic regression, again, it is the type of variable that decides. If the outcome is 2 levels, such as mortality, yes, no, some people die, some people survive. So I use logistic regression. If the outcome is continuous, such as quality of life or length of stay in the ICU or whatever it is, that is a continuous variable, then I use linear regression. And this is the end of my presentation. I'll be happy to answer any questions you might have.
Thank you very much, Dr. Hani, for this great presentation, very insightful and huge topic, summarized very nicely in this presentation. We'll open it for open floor for questions. People who wants to have who have a question can raise hand. There is a little button on the says raise hand. If you raise your hand, we'll unmute your microphone and you can ask the question.
Perfect.
I think I would start maybe with a question about the measures of association. You mentioned the relative risk and odds ratio.
Yes.
When do we use this and use the other one? Is there a certain areas we use this, not the other one?
All right. So the relative risk and the odds ratio are both measures of association. I'll go to the slide and then present it. Just 1 second. Okay. Do you see my slide, Dr. Arabi?
Yes.
Okay. So both odds ratio and relative risk are measures of association. In other words, we are testing the association between 2 categorical variables. Now, the thing is, in some study designs, it imposes on us to use one or the other. For instance, if I'm doing a prospective cohort study or a follow-up study, I can talk about risk because by definition, risk is the probability of something that will happen in the future. That's why I measure, for example, 2 people over the total, okay? Now, but sometimes we do retrospective studies such as case control studies where the outcome has already occurred and it doesn't make sense to talk about risk. So instead of talking about risk, we talk about odds. What does odds mean? So instead of dividing 2 over 22 2, I divide 2 over 20. So in this way, I adjust for the concept of, for the fact that the outcome has already occurred. And then I divided not by 4 over 36, but by 4 over 32. What's really nice about the odds ratio is that the interpretation is most of the times very similar to the relative risk. If it is 1, it means no association. Less than 1, it's protective. More than 1, it increases the risk or the chances. Now, another reason why we use an odds ratio is when we are doing the multivariate analysis. So as you remember, I showed you here the logistic regression. When the outcome is 2 levels, by default, the outcome from the logistic regression is an odds ratio. So when you do the analysis using a logistic regression, you will get an odds ratio, and that's why you have to know how to. Does it answer your question?
Yes, very much.
Okay.
Any questions from the audience? So the logistic regression is results are expressed as odds ratios. How about the linear regression? How do you express the results?
Okay, so the linear regression, usually we express it as a slope or as a beta. So remember, the outcome is continuous. So let us say I'm interested in the effect of age on length of stay in the hospital or in the ICU. Okay, so both of them are continuous. So if I go to the previous slide, when I looked at this, for example, there is a line. I want to know how much does Y or how much does length of stay in the ICU change with every 1 year change in the age. So as age increases by 1 year, how much do you expect that the patient stay more in the ICU? Or every 10 years increase in age, how many days or hours or whatever it is, the patient is expected to stay in the ICU. And that's why we call it the slope. So if we draw a line, such as this one, assume that this is the line, the slope is the change in Y with every unit change in X. So it is called a beta or a slope.
Very clear. Thank you.
Okay.
One more question about the correlation. Maybe if we can go back to the, I think just immediately, yeah, this slide.
Okay.
What's the R refer to? So does it refer to the slope or the degree of correlation or what? So for example, the one highlighted with red, the slope actually looks very much similar, but they are kind of dispersed. So what the R refers to? Yeah.
Okay. The slope is dependent on the variable you're talking about. So sometimes the slope might be, I don't know, 5 or 10 or 50 or 60. Depends on what variable, what are the units of the variables you are talking about. So the slope is something else. Now the R is an index. It is a calculation that people put, similar to probability. Probability is ranging from 0 to 1, right? So people said that 0 is this and 1 is that, and anything in between is what indicates the probability. So the correlation, to reflect on, sometimes it might be positive or negative, they did it between -1 and +1. And 0 is where there is no correlation. And if I'm not mistaken, it is the relationship between each point and the line that you have. For instance, if I do this line, the first, this is the line, right? So yes, there is no distance between each point and the line. But if I take this one, there is a difference between this patient and the theoretical line that falls here.
Mm-hmm.
So it indicates how far people are away from the line, and that's why the higher the R, the more closer they are to the line, and the smaller the R, the further away they are.
Very nice. Can you go to the next slide, which also illustrates, yeah, this one. So the slope is reflected in, so the R is how far from the line.
Yeah.
But the slope is reflected.
The slope is not
number.
indicated here. The slope is not indicated here. We don't have the slope. But the slope, theoretically, we get the slope only from the linear regression. We don't get it from correlation.
I see. Okay.
So
Okay.
again, it is how much this is angle and this is whatever loan in PLA. So how much does this change with each one unit of this? If it changes from 4 to 5, what happens to the Y?
Yes. We have a question from Dr. Abdurrahman Al-Asiri. Can you unmute yourself, Abdurrahman?
Hello. Thank you for this informative lecture. Just I have two questions. Could we have two tests in same study, chi-square test and t-test also in same study, or just one test we use? And the other thing,
yeah,
and the other question, as epidemiologist, which prefer program using, R program or spaces? Which program you will use to be easy for also as a physician to use?
Now, this is a study that we carried out, Dr. Arabi. I'm not sure, Dr. Yassin, if you remember this. You see that you have here age and the tertiles for caloric intake, 0.02, and we have underneath it sex and the tertiles, which is 0.54. Now, each one of these is calculated by different tests. This is calculated by the t-test because I have categorical and continuous. The next one is calculated by chi-square because it's categorical and categorical. So absolutely, in one study or one paper or one table, you might have 2 or 3 or 4 different tests. You do the test based on the variables that you have, on the distribution that you have, and so on. So yes, of course, you can have multiple tests. Now, the second question that you had regarding the program, there are so many programs. The most frequently used one is the SPSS, which is the Statistical Package for Social Sciences. The reason why it's popular and people like to use it is because it's very easy. We used to carry out workshops on SPSS. In 2 days, you'll be able to do most of the analysis that people require. Because it's drop buttons. So you just go to the menu, tick, 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 and you will be able to get the p-values and the analyses that you want. Now, of course, there are some more advanced or sophisticated programs, such as the one that we use with Dr. Arabi, such as SAS, Statistical Analysis Software. There is Stata, there is Statistica, and so many others. But I would recommend for physicians, SPSS is good enough.
Agree. And actually, it has good amount of advanced statistics.
Oh yes,
So
yes,
it's really advanced. So it's a great software. Okay, I think we are. This has been great presentation and very insightful. I'd like to thank you on behalf of the Saudi Clinical Trials Group for this presentation. I'm sure many of the audience, doctors, nurses, and residents will benefit from this for their projects. So thank you again and have a good night, everyone.
Thank you, Dr. Arabi, for inviting me, and we'll be in touch soon, inshallah. Assalamu alaikum.
Assalamu alaikum.